I got one for you. What happens when the theory of the large meets the theory of the small? In this case, what am I talking about? The theory of the large, Einstein's general theory of relativity. That's our complete understanding of cosmology. It alerts us to the nature of the space-time continuum that spans the universe. The theory of the small, of course, it's quantum physics. Quantum physics. These two theories apply in their own regimes. Quantum physics, the theory of the small. General relativity, the theory of the large. Yet they are fundamentally incompatible. Quantum theory requires that space and time be quantized. That's what quantum theory means. That space and time are not infinitely divisible into a smooth continuum. It actually breaks up into pieces, and you can't get pieces any smaller than that. Meanwhile, general relativity requires that space and time be smooth. Like I said, they both work in their own regimes, but you can ask the question, what happens if they have to meet each other? What happens if they have to operate in the same place at the same time? Just such a situation existed in the very early times of the universe. In the early times, the universe, as we know, is expanding. That means yesterday it was smaller than it is today. You go back early enough, there's a point where the entire universe was in the same place at the same time, occupying an extremely small volume. A volume small enough that it rivals the scale over which quantum physics applies. The entire universe within the size of an atom. Under those conditions, what do you have? You have like a shotgun marriage between these two incompatible theories. Something's got to give, because the large becomes the small. Well, the effort to merge these two theories, these two great understandings of our universe, comprises part of what the work that string theorists do. Among other things that they're up to, that's a big part of it. Can you merge these two great theories of the universe? And what this spawns are ideas, really freaky ideas like quantum foam, where the fabric of space and time is so tightly curved onto itself that space-time is less like a smoothly curved fabric and more like the froth on a latte. In this state of matter and of energy, quantum fluctuations, which are a normal part of quantum physics, they can spawn entire universes. Since a universe is the size of an atom, a quantum fluctuation births an entire universe, each with slightly varying laws of physics from each other. And all this unfolds in dimensions higher than our own. Now, not all universes will survive the laws of physics they've chosen for themselves. Some will recollapse before stars are born. Others will expand so fast that matter never has the chance to coalesce into galaxies and stars. And still others might succumb to laws where no matter is stable at all. We're in the one that allowed some of the matter within it to achieve consciousness and to contemplate its very existence. If quantum fluctuations give rise to multiple universes from within that quantum foam, then what do we call this entity? Multiple universes being born? The multiverse, of course. The multiverse. I've given some of the theoretical arguments in favor of it, but there's also historical, philosophical arguments in its favor as well. Let's go back in time. There was a day when Earth, pre-scientific era, there was a day when Earth was imagined to be all there was. everything else orbited around us. So Earth was singular, unique, large, and important. We would later learn that Earth is just one of many other planets. The planets that we saw in the night sky were not something smaller and lesser than we are. In fact, among planets, we're actually quite small. Jupiter has storm systems in its atmosphere bigger than the entire planet Earth. So that'll set you straight right quick once you make those comparisons. So we learned that there's not just one Earth, there are many planets in orbit around the one sun. Of course, our sun is special, it's big and it's bright. And look at those stars in the night sky, they're just small and dim. No, they're just far away. In fact, the sun is not even unusual among stars. It's not the biggest or the smallest or the brightest or the dimmest. It's kind of average, actually. So we learned that our sun is just one of countless other suns, evolving in our mindset from a time when we imagined the sun to be unique in the galaxy. How about the galaxy? The Milky Way. We see the band of light in the night sky. Surely that's unique, yeah. We're the one galaxy that comprises the universe. Nope. As we've said many times, Hubble showed that our Milky Way galaxy is but one of countless billions of galaxies in the universe. The universe. How about the universe? Surely there's only one of those. There we go again. You want the universe to be singular? Nothing before this has ever been singular, in spite of our urges to require that to be true for them. In fact, as far as we can tell, there's nothing in the universe that comes in ones. Perhaps not even the universe itself. So, this actually gives us a place to stand regarding that perennial question, what was around before the universe began? Perhaps we began as a single quantum fluctuation among countless others in a hyperdimensional multiverse. But, of course, that just shifts the question to a new paradigm. What was around before the multiverse? Or, better yet, if indeed the universe never makes anything in ones, not even the universe itself, then perhaps the multiverse from which we are born is part of a system of multiverses, and that part of a system of those, and so forth. Given that we started all this thinking that Earth was something special in the center of the universe, it can be quite a blow to one's ego. But only if your ego started at the beginning of the day much larger than the cosmos can justify. So we take this fact and use the trend line in the history of our discoveries to try to never have an unjustifiably large ego. Because just wait a few decades, at most, we're going to find something about the universe that puts us in our place. And such is the continued progress of our discoveries about our place in the universe. In the early universe, we know that everything was packed into a small space and the temperature was very high. And when you have a high temperature, the world around you behaves very differently from what goes on here on Earth. There's an equation that matters that drives everything, and we've learned this equation in elementary school. It is, of course, E equals mc squared. Hold the c squared aside for a moment. That's just a constant, and it happens to be the speed of light. What matters in that equation is that energy is recognized to be equivalent to matter. You can convert them back and forth at will, provided you have enough energy to pull it off. And when you do so, you can create particles out of energy fields and energy fields out of particles. This was going on incessantly in the early universe because it was just that hot. Now, how does that work? Well, light, anywhere you see it, typically visible light, doesn't have enough energy in it to make particles. That's why E equals mc squared does not manifest itself in any obvious way in everyday life. But if I was instead being bathed not with visible light, but with high energy X-rays or gamma rays, that's light too. X-rays and gamma rays, that's a high energy version of visible light, okay? That kind of light has enough energy to spawn spontaneously. It can create particles, electrons, for example. Now, there's a symmetry to this. Symmetry is a beautiful concept in the universe. What we have found is that if you take light and make matter out of it, the energy from light, and turn it into matter, it makes pairs of particles every time. If you take a high energy X-ray, it'll make an electron and the antimatter counterpart to the electron, the positron. It'll spontaneously create them and they'll fly apart in opposite directions. If you bring those two particles back together, they annihilate and become energy once again. This is E equals mc squared manifested. And it does this all the time in the early universe, and it's a kind of an equilibrium particle soup that went on back then. All right, so here's what happened. Every time you make particles, they come in pairs. Every time they annihilate, they disappear completely. If that's all that went on in the early universe as we expanded and cooled, there'd be a day where every matter-antimatter particle annihilated, it would create light. That light would cool, wouldn't have enough energy to make particles again, and the entire universe would be just filled with light and no matter in it at all, because everything was symmetric. All matter got annihilated with its antimatter counterpart. All particles got created in pairs. So if symmetry, which we know and love, that drives so much of the laws of the universe, if symmetry were preserved, we wouldn't be here to talk about it. So something must have happened in the early universe, and we call it symmetry breaking. Nature disobeyed its own laws. At some point, a high energy beam of light created a matter particle without the antimatter particle pair. That's a breaking of the symmetry. And we know how often this must have happened. 1 in 100 million of these phenomena gave us a matter particle and no antimatter counterpart. This matter particle now will live forever because it's got nobody to annihilate with. All the others annihilate. So in fact, the universe that we see, know, and love today is the consequence of broken symmetry in the very early universe, shortly after the Big Bang. It's a mystery. We don't know why it happened. We try to produce it in the lab. Everything we do in the lab is symmetric. Anytime we create particles in the lab, it's a matter-antimatter particle pair. Every time we put them back together, we get light. So something happened in the early universe. We call it a phase transition. You're familiar with phase transitions in everyday life. Water goes to ice. The fundamental properties of it changes across that border, the freezing point. Water can go to steam. That's another phase transition. So when we think of periods in the early universe where things were really different on one side of a transition from the other, we call that a phase transition. In that particular case, it was the breaking of the symmetry of the matter and antimatter in the cosmos. So I bet you never thought that you would embrace and love the fact that while we have antimatter, there's a point where, unless nature breaks its own rules, we wouldn't even be here to contemplate the fact that it broke its own rules. far as we know, nothing can travel faster than the speed of light in a vacuum. Period. Okay? It's not like we haven't wanted to make that happen. It's not like we haven't looked around the universe to see if we can find something that violates that rule. We have. We've looked hard. We've never found anything to violate that rule. Not only that, it is a fundamental tenet to Einstein's theories of relativity. Okay? So what that says is this speed of light rule is not a limitation of technology. It's a basic fundamental feature of the universe. Now, you might be thinking, look, you guys once said we'll never be able to fly with heavier than air hardware, or you will never break the sound barrier. We'll never go faster than light. You know, this is where I hear this all the time. Except these are fundamentally different statements. What's different about them is the people who said we will never fly fast, that we'll never fly. Well, okay, when they said that, surely there were birds flying overhead. Surely. So it's not like flying is impossible. You just haven't figured out how to do it yet. All right? That should have been obvious to that person. That statement should have been, we have not yet figured out how to fly. And birds are heavier than air and they manage it just fine. And this thing will never travel faster than sound, the sound barrier. Well, we had rifles at the time people were saying that where the bullet coming out of the rifle traveled faster than sound. We had the bullwhip. When you flick a bullwhip, the very tip of the whip, the reason why it makes that cracking sound, that's like a mini sonic boom. It is traveling faster than sound. We had things that travel faster than sound. Just because you couldn't figure out how to make an airplane do it, that's not my fault. Not the fault of the universe. So those two claims are fundamentally different from the assertion that we will never go faster than light. Doesn't mean we haven't thought about it. In fact, there's a hypothetical particle that was invented just to accommodate what would happen if we went faster than light. And they're called tachyons, from the Greek root of that word meaning speed. A tachometer has the same root as the word tachyon. These are hypothetical particles. We've never found one, but we imagine, what would it be like if particles existed faster than light? Well, it turns out Einstein's relativity tells us you can't accelerate any material object to reach the speed of light. But if you put in an object that exists faster than light, you can still run through all the equations, and the equations don't mind. But some interesting properties emerge. For tachyons, what do you get? They exist faster than light. It will require an infinite amount of energy to slow them down to the speed of light. So in fact, they can never reach the speed of light. And because they're going faster than the speed of light, they live backwards through time. How would you ever detect such a thing? Well, here's what you do. You find out what kind of interaction your tachyon would have with particles that exist in your present. So as they go backwards in time, they have to share your present, even if for only an instant. So we looked at what energies the tachyon would have, what particle interactions might be favored for a tachyon. We've looked for them, we've never found it. And so to this day, a tachyon remains an intellectual curiosity that itself does not violate any known laws of physics because it's not crossing the speed of light barrier. It's existing faster than it. But the day we find a particle faster than light, we bet pretty sure that it'll have all the properties that I just described, which would make it one of the coolest particles ever discovered. Now, there are other ways to go faster than light. You can cheat in a legal way. For example, on Star Trek, everybody's favorite sci-fi series from the 1960s, Star Trek. What did they have? They had warp drives. Warp drives. What did that do? Well, here's your galaxy right there, and they're on one side of the galaxy and they want to get to the other. So what do? They turn on the warp drives, and that takes the space-time continuum and bends it. And now here's where they are, and here's where they want to go. They just take a little gap through the fabric of space-time, unwarp the galaxy, and there they are. They cross the 100,000 light-year diameter galaxy during the TV commercial. Works every time. So that's legitimate in the sense that we know space and time can curve. And if you can control that curvature, you can get to a place much faster than a light beam would have taken. In time, much less time than it would have taken a light beam to traverse that same journey. And so that's we allow that. That's a cool, I want warp drives that can do that. That would be really cool. But not only that, this little path that they took to cut from one part of their space-time to another, we have a term for that as well. It's called a wormhole. That is a portal in the space-time continuum that takes you from one part of the universe to another. And the more energy you have, the more you can curve major sections of the universe to traverse great distances. And I assert that if we're ever going to travel the stars, if we're ever going to cross the galaxy or visit another galaxy, it's going to have to be in some kind of way that exploits wormholes and the curving of the fabric of space and time. It's going to have to, because our fastest spaceships, if you hop a ride on them today, would take you 50,000 years to reach the nearest star to the sun. And the nearest star to the sun is sitting on our nose compared with the scale of the galaxy. So, watch that space. Look for the invention of a warp drive, because I'm going to be on that first spaceship that has it. You ever wonder what the long-term fate of the universe is? We think we know enough of the laws of physics and the behavior of stars and galaxies to actually have some insight into what that looks like. Because stars don't burn forever. Stars will not continue to be made forever. There's a winding down of the cosmic clock that we know enough physics to be able to track. So, let's go forward in time. One of my favorite moments will take place in about 7 billion years. We chatted about it a few lectures ago, and that was the impending collision between the Milky Way galaxy and Andromeda. Galaxies all around the universe, if they are within each other's gravitational embrace, they will ultimately collide. This is the very distant future. Some galaxies look like they're on a stable orbit around each other. But there's an erosion of that orbital energy that is happening with any two orbiting objects. They will eventually collide and merge. Okay, how about the gas clouds that are generating stars? Eventually, we're going to run out of gas. Our galaxy, about, 10, 20, 30% of its mass is in gas, and it is cranking out stars. There's some nearby fascinating regions of star formation in the sky tonight. Okay? So we keep making stars, so everything feels like it's in equilibrium. Stars die, other stars are born. The problem is, for every star that's born out of a gas cloud, most of those that are born don't return their gas into space. It gets locked up. And so every time you make a star, you are draining the supply of gas clouds. The day will come when there's no gas left. All the gas supply is exhausted, and the era of birthing stars will have stopped. Now, that is 1 trillion years from now. Don't hold your breath. It's a while. Don't worry about that. However, right about then, something else will happen. Remember this dark energy I've been telling you about that's forcing the universe to accelerate? You got to realize that that acceleration is catastrophic. It will take every galaxy in the expanding universe, and in a not very much time from now, it will accelerate them beyond our horizon. Now, let's back up for a minute. Let's back up. Before Edwin Hubble showed that the fuzzy spiral things in a night sky were not just fuzzy spiral gas clouds among the stars. They were entire other galaxies beyond the stars of our Milky Way. But before that moment, we would sit out under the stars, look up, and imagine that those stars was the entire universe. That was the state of mind at the time. It was not until Hubble where we learned that there are other galaxies out there. It's an interesting transition in our understanding of our place in the universe. Now, what effect dark energy has in the rapid expansion of the universe is that all the galaxies of the night sky recede so fast that they go beyond our horizon. What is a horizon in the universe? It's just kind of like our horizon here on Earth. You put a ship out to sea, and it looks out to the horizon, and is that the edge of the Earth? No, you know better. You can travel in that direction, and you see more Earth come into view. But at any given instant, there is an edge beyond which you cannot see. And if a ship goes across that edge, it is gone from your sight. That concept of a horizon at sea has much in common with our three-dimensional horizon in the universe. And so, here's what will happen. As these galaxies accelerate beyond our horizon, there's an important chapter in the history of the universe that will get erased, torn from the pages of cosmic truths. Without galaxies in our night sky, any post-apocalyptic Earth civilization will know nothing of the cosmic history of the universe. It'll be the end of cosmology. Everything we know about the beginning of the universe comes from studying galaxies, not from stars, galaxies. And what will happen at about that time in the future of the universe is that anyone on Earth or in our galaxy at all who looks up at the night sky, that night sky will resemble the pre-Hubble night sky. Except the difference is, back then, they only thought the stars in the night sky was their entire known universe. Whereas in our future, the stars of our night sky in our own galaxy will be the entire known universe. There'll be no galaxies available to us. That's an interesting chapter in our lives. Because if we're trying to be scientists, if we're trying to be astrophysicists, if we're trying to be cosmologists in that time, there's a chapter missing. There's a piece of the universe not available to us. There simply would be no cosmology at all. Get back to that in a minute. Let's continue to evolve the universe. All right. Eventually, without any stars to do the replacing, the stars end up burning out one by one. They turn off in the night sky. The sky starts getting dark. Eventually, we theorize that the proton will decay. The very structure of matter itself will decay into lesser, lighter particles. That's bad. That's bad for matter, okay? That's way in the future. Now we're talking at least 10 to the 33 years. That's huge. I'm talking about the very distant universe here, okay? Very distant. I'm self-aware of this. All right. You keep going far into the future, all the orbits of galaxies decay. They spiral down ever so slowly, but they'll eventually get there and pile onto the central black hole that lurks in the center of every single galaxy. So every galaxy loses its stars. The remnant cores of each star that burned out eventually spiral down into their black holes, and you have this sea of black holes in the universe. Those black holes eventually evaporate using Hawking radiation. They evaporate. That takes 10 to the 100 years. That's a Google years. Google spelled G-O-O-G, OL. That's the original spelling of Google. Got nothing to do with the company. The mathematicians had that word first. So, what is going on? The black holes evaporate, stars are gone, the universe is dark, and as it expands, it continues to cool, and the universe plunges towards absolute zero. During this expansion, as it cools eternally. What this tells us is that no, the universe will not end in fire, but in ice. All right, now let's get back to my night sky that's missing galaxies. On the short list of what keeps me awake at night, I ask, is today a time in cosmic history where some chapters in the cosmological storybook have been previously removed? Today, I ask that. I know that in the future, we're not going to have cosmology because there'll be no galaxies. Is there something we don't have today and I don't know we don't have it today? And I'm trying to figure out the universe and I'm missing an important chapter. I'm missing the rule book. I'm missing the index. I'm missing the primer of how to figure out how the universe works. Because if we are victims of such a gap in the data on the universe, then we're surely just groping in the dark, delusionally thinking that we've been granted full access to the universe. We want data. We need data. We require data for us to deduce the correct operations of nature. And so I ask, is our ignorance that prevails today, that we're only 4% of the universe and the rest we're clueless about, is that state of ignorance the consequence of a missing chapter in cosmic history? Or is it just the next set of mysteries awaiting the birth of a new Newton or an Einstein? Or perish the thought, maybe in this particular case, the human intellect is insufficient to answer the very questions that it's smart enough to pose.